In this session, I think I can promise you some fun, some weirdness. You'll get a pretty strong taste this time, say more so than most sessions, of how weird quantum mechanics can be. Like, remember, I think I said in the very first session of this quantum mechanics course in Lecture 1 that we human beings, we live on a kind of 1 meter scale. That's roughly in order of magnitude, that's our size, right? So we have no daily experience of phenomena that occur at the atomic scale, which is 10 of the order 10 billion times smaller, right? So the way nature behaves at those tiny scales is just utterly alien to us at the 1 meter scale. So I think today, in this session, you'll get a taste for how weird quantum mechanics can be. All right. Well, I'll just finish up a little bit about when the particles are assumed to be distinguishable, so you can tell one particle from another. They have different properties of some sort, and they don't interact. In that case, the eigenvalues, the energies for each individual particle, having its own individual Schrödinger equation, its own individual psi function, those energy eigenvalues, EI, where I is the ith particle of n, you can sum those energies here. So you can sum those energies here, these eigenvalues for each particle, to give you a total energy, big E, which is the eigenvalue for the wave function, capital Psi, which is the wave function for the whole system, for all n particles. Right? And that makes sense when you have no interaction and you have distinguishability. But, and I've got a big but here, ... If your particles cannot be distinguished, right? So in other words, they're indistinguishable. They're identical. So you have identical particles. Like, imagine you have n electrons, right? Can't tell the difference between them. So this is where the interesting mathematics and quantum mechanics starts. You probably noticed how quickly that just fell off my tongue. I guess I have deep grooves in my brain combining those two terms, quantum and computing, because that's one of my strong intellectual interests. Fascinated by the possibility of quantum computing. One of my research goals, I'm hoping once I really understand very high level stuff, I may, it's just a hunch, it's a research goal, future, and if you're interested, you may be interested to follow this up as well. The goal is to find phenomena in physics, perhaps topological type physics, where the change in the phenomena is occurring at a larger rate than 2 to the power n. Now, in quantum computing, a quantum computer can outperform a classical computer by a factor of about 2 to power n, so exponentially greater, where n is the number of quantum bits or qubits in your quantum register. Like, imagine a string of electrons of different spins. So that string, that would be your quantum register. Register as in quantum, as in computer science, like a string of bits connected to each other. So I'm trying to find phenomena where things are changing at a much faster rate, greater rate than 2 to the n things changing at the same time, as in quantum computing. And if that's possible, then maybe, and here's the big hunch, and be a big dream if it could be done, to compute at a more powerful with a greater level of complexity than just 2 to the n. Maybe I don't know, maybe 2 to the 2 to the n or something. So I need, mathematically it's easy to find expressions with higher powers than 2 to the n. I mean, that's trivial. But trying to find physical phenomena that operate at rates at complexity levels larger than 2 to the n, that's less easy. And even if you can find them, then you need to be able to figure out how to compute with them. Anyway, so this idea is on my back burner. It's at the back of my mind. Been there for years. Just fascinated with the possibility of finding a kind of super quantum computing, superior to the power of 2 to the n. Anyway, that's a side issue, but a fascinating one. Okay, all right. Well, so protons, neutrons, photons, all these categories of elementary particles. Well, it's debatable how elementary they are. For example, protons and neutrons are not fundamental in the sense that they do have constituents. They have smaller components that create the proton. For example, proton has 3 quarks. The neutron also has 3 quarks, a different combination of quarks. But so the quark, is it fundamental, or do the quarks have constituents? If you look through the history of particle physics the last century or so, we've just gone down from layer to layer to layer. We just keep peeling off another layer of nature's onion, in a manner of speaking. Anyway, so protons, neutrons, photons, whatever, they're all indistinguishable. So that means, if you think about it, if you take your capital Psi, which is a function of, well, it's in the previous session, but remember that Psi was a function of R1, R2, ... Rn, where each of those position vectors, R1, R2, they refer to the position of particle 1, particle 2, ... Okay, so now swap. Now this is sort of a thought experiment, as the Germans call them, or Einstein really loved these kinds of experiments. Gedanken, remember I speak German, Gedanken experiment. Gedanken just means thought, thought experiment. So it's a kind of experiment, plausibility experiment you do in your head. So imagine now you've got this wave function that's applicable to the whole system, to all n particles. And let's say they're all electrons. Imagine you've got n electrons, indistinguishable. So if you swap 2 of them, swap them around in position. So particle 2 now has position 1, and particle 1 now has position 2. Now because they're indistinguishable, this psi function for R2, R1, ... should be just the same as the psi function for R1, R2, ... Right? In other words, your psi function here for indistinguishable particles, if you swap 2 of them, this should stay the same, right? Because you can't tell the difference. If all these particles you've got are in positions R1, R2, ... Rn, and you just take 2 of them, swap them around, it's the same system, right? Because they're indistinguishable. Therefore, when you permute 2 particles that are indistinguishable in your n-body, your n-particle system, multi-particle system, it should be the same. So, so in terms of your probability densities, let's say we have just a 2-particle system, but identical, 2 identical particles. Then capital Psi R1, R2, or squared, so that probability density, should be just the same as big Psi R2, R1, right? So if you're swapping around the 2 particles, particle 1 now is at position 2, and particle 2 is now at position 1. You just took the 2 particles and swapped them. Okay, so you should get this. So the square of this should be equal to the square of that. Now you've got 2 possibilities, to solve this condition, which seems very plausible. It makes sense. But as we advance, you'll find the math, when you're trying to interpret the math, it gets weirder and weirder. Okay? So anyway, so this capital psi, you know, the two-particle wave function, you know, let's just call it that. So this is now the two-particle wave function. So when you square it, it should be just the same as the two-particle wave function with the two particles swapped. Right? Because the two particles are indistinguishable. So this should be equal to that, right? Now there are two solutions to that. I mean, think about it just in mathematical terms. A squared equals b squared, right? So therefore, A can be b, or it can be minus b. Okay? So in math terms. So these two-particle wave functions, same story. So either you know, A equals b, if you like, or A equals minus b. So either the two-particle R2, R1 is the same as R1, R2, or if you swap them around, you get a minus sign for the two-particle wave function. You get a minus sign in front of it. So and the other possibility is that psi R2, R1 is minus psi R1, R2. Okay? Just from simple math.